you can neglect it.
So the process is really theorized to be that the hydrogen hits the surface, that energy breaks the bond, then it hits two active sites, not that it comes near an active site, ejecting the active site's greater, so it has to leave the hydrogen to become multivalent.
You're in the realm of research at that point. There are people who will say that the difference between dissociative and molecular adsorption is that dissociative adsorption occurs with initial contact with the metal surface. But there's plenty of research papers you can go find for hydrogen that says, no, fizzy-sorbed hydrogen is a thing. You first fizzy-sorb, and then it simply reacts so quickly you never noticed it before. And in fact, even molecular adsorption, there's often a very, if tiny, barrier associated with a molecular adsorption. Even though you're not breaking a bond in molecular adsorption, you are rearranging electrons, which can lead to a small barrier. Yeah?
So that small barrier would imply there's some sort of transition state.
Yeah, there's a transition state.
What would that look like, though?
It would look like...
When you consider a transition state, there's like weird half bonds.
Yeah, in this case, it's not a bond-forming transition state. It's an electronic reorganization transition state. So you might be able to tell by the internal structure. For example, with CO, the CO bond does get longer upon adsorption. You might be able to tell because it's having to push stuff away from its active site. But again, this is far outside the assumptions within Langmuir, because Langmuir assumes that sites don't interact. Yeah?
Didn't you prove that hydrogen fizzy-sorbs by forming a multi-layer?
No, I mean, you can, and people have. But then they're just going to say that under those regimes, you're not capable of dissociative adsorption. So you're using a flashlight to see, or you're changing the system properties in order to see something. And a very classic thing in research is somebody does that, and you go, well, yeah, you change the properties, so you change the outcome. That's everybody does that. I've done that. You study that problem at low coverage, which is meaningless, because the real problem is at high coverage. And then they go, well, I can't study it at high coverage. I'm an ultra-high vacuum guy. And I go, yeah, well, sorry. Doesn't mean what you found matters. And it does often, but I have made that statement. I have published data. I had a talk at, I don't know, one of the national conferences, and Gabor Summerjai, nobody in this room will know who that is, but he's a guy at Berkeley who was on a short list for a Nobel a very few short years ago. And he gets up and he has this whole big thing. Everything happens at defect sites on metal catalysts. Everything happens at defect sites. I think it was my second slide where I said nothing happens at defect sites, and the people who tell you this are because they only look at low coverage systems. And I was right after him. He told me I gave a good talk, but shit and kittens. All right, so the rate for dissociative adsorption does change. Because you have now this A plus 2 star goes to B star plus C star. I'll do it for hydrogen too, because it makes more sense to me when I see real atoms. Because there's 2 sites involved, okay, it does alter, and because I'm making 2 adsorbates, it does alter the rate of adsorption in this manner. So you get, this is little k again, pressure, now you have a concentration squared, right? Concentration of vacancy squared, because I have to use 2 sites. Minus the concentration of Bs times the concentration of Cs divided by big K adsorption. And again, if these are both hydrogen, then this would say the concentration of hydrogen atoms, not dihydrogen, but the hydrogen atoms on the surface squared, right? Again, this is B has to react with C to go backwards. So that's why you have this product of concentration. So again, this is dissociative adsorption. Still reversible, that's why I have the minus, and still with all of the assumptions inherent in Langmuir. I haven't changed any of the assumptions we used, and that's the equation you'll get. And so at equilibrium, you get big K times the pressure to the 1/2 times the concentration of vacancies is equal to the concentration, in this case, of B. And the concentration of B for this reaction is equal to the concentration of C. And again, this B plus C, which is the general way of writing this. Not all of the dissociative adsorption involves something like hydrogen that makes two identical fragments. You can dissociatively adsorb, for example, methane. And in that case, it makes a methyl and a hydrogen. Okay, so now what happens if I look at the coverage or the concentration as a function of pressure of A? What type of shaped curve will I get? So let's again think about the extremes. What's it going to be at very high pressures?
Very low coverage, B.
High coverage. This is A goes to B.
Oh, A goes.
Yeah, it's in the earlier one where we're reacting. This is the one where we are dissociating. And this works pretty much the same for molecular adsorption too. So what's it going to be at very high pressures of A? What's the shape of the curve going to look like? It's going to approach a constant value. Why?
There's only so many vacancies on the site.
I have filled my surface, right? So I know I'm going to approach a constant value. If this is coverage, that would have a coverage of 1. Of course, concentration won't be 1. That would be
What does it say below CBS?
or coverage.
Okay.
Yeah, a lot of times you'll see these plots with coverage instead of with concentration of adsorbed species. What about over here? Linear, squared order, it look like this. Is it decaying? Is it a straight line? What's it look like when we start?
By the exponential start.
Say linear?
Are we assuming it's always rate limited?
That doesn't matter. This is the, sorry, I should explain a little bit better. This is going to be your equilibrium coverage. So no, you're ignoring rate limitations. This is, I put some contact of A, some pressure of A in contact with the surface. What is the coverage after enough time that I'm at equilibrium? So this isn't a rate. This is just look at this. So it starts out first order, and then it's going to bend over. So this is a Langmuir isotherm. Now what if I increase the temperature? So let's say this is at T1. And now I go to T2, which is higher than T1. What does the shape look like? Does it go up?
A little lower.
It'll go lower. Why?
We'll get there faster.
If it's getting there faster, where's time up here? There's no time.
You have fewer moles per pressure.
Oh, then
Why?
top.
But you can
Why would I have less adsorbed species at the same pressure if I'm at a higher temperature?
One thing will be in the gas. You increase the-
Why?
You decrease the temperature.
If I increase the temperature, I'm making the entropy more important. Upon adsorption, I always lose entropy. I have something that can move around in all 3 dimensions in the gas phase. I'm putting it on a surface where at best I can move in 2 dimensions. At best. Normally things bind even stronger than that. So as you increase the temperature, the amount of stuff on the surface at that same pressure will decrease. Now, does the asymptote change? Am I approaching a constant here and then here? Or does the asymptote stay the same, it just takes a higher pressure to get there? And it does, yeah. These, don't be confused by my drawing. These are still going to go out to the same total concentration.
So,
It just means that I need more pressure to convince the atoms they should go on the surface, not be in the gas. Yeah.
But isn't he also right that if you're operating the same pressure at higher temperature, you don't have fewer moles of gas? Right?
Say that again. You're operating at the same pressure.
Pressure,
I go to a higher temperature.
like you have to have a lower number of moles.
Why?
Because like ideal gas would put as PV over RT, so.
Oh, you're saying the concentration of gas changes?
Yeah.
Yeah, but that only shows up in my rate. That doesn't show up. in my equilibrium. You're describing the rate of adsorption. I'm asking how much is there after equilibrium.
Okay.
That only affects the rate, not the thermodynamics. Yeah,
So, is temperature make stuff not stick?
exactly.
That's it?
I mean, think about water. If I heat water up, it leaves. It's not that different. Adsorption is not that different from condensation into a liquid. It's not that different. Yeah.
So do you ever have to worry about your pressure being so high and you introduce condensation?
Of what sort?
Well, as in like, the pressure's just so high at this constant temperature that it would change phases, so it would become a liquid instead of staying as a gas.
Yes. Absolutely.
But
Yeah,
wouldn't
you'd have to
it
worry about
still-
that.
How would you affect, how would critical phenomenon happen here? Like, assuming you went to even higher and higher temperatures.
So when you do real isotherms, a lot of times what you'll see is this type of shape. This is chemisorption. Then you kept going. You start condensing, doing physisorption, multi-layers. So more and more is uptook. Technically, the way that I wrote this, those species wouldn't be counted in this plot.
Okay.
But in reality, the way that you do these measurements is you look for how many atoms, how many molecules are missing from the gas phase. So you would count any physisorb species, but usually that happens at a higher pressure. Because they don't have that chemical driving force, you have to go to a higher pressure to see that physisorption. And physisorption and condensation are right next to each other in terms of physical phenomena, especially when you're talking about multi-layer adsorption. Yeah.
Now, what if you were to operate above the critical temperature so you wouldn't have condensation in the classical sense?
Yeah, if you're doing supercritical processes, you can still model adsorption, but obviously a lot of things are a little bit, or you have to treat them a little bit fuzzy because it's not technically vapor or liquid.
Is it possible to get a multi-layer if you're above the?
Oh yeah, sure. Yeah, I mean it couldn't be so big, but imagine that I'm in a zeolite, and so the multi-layer is not just interacting with the adsorbed species, but it's also interacting with the pores and the walls of the zeolite. And there's enough interactions there that cause condensation.
There's no homework over break, right?
There will be homework, but it won't be due until Thursday. So when we pick this up, we're going to talk about more about the Langmuir model, and then like just one page of notes, and then